Welcome! Our world is just full of sequences. Think about it. The words in a sentence, the notes in a song, the steps you take in a recipe. It all makes sense because of the order it's in. But how on earth do we teach a machine to get that? To actually remember what came before? Well, the answer might be sitting right in your hand. Yeah, really think about that for a second. You type, "I'm heading to the," and boom, your phone suggests store or gym or office. It's not just pulling words out of a hat. It somehow understands the context of what you've already written. So how does it do that?
You see, for an AI, this is a really unique problem. Most standard neural networks just see all their data at once, kind of like dumping a jigsaw puzzle on the table and seeing all the pieces scattered around. But for language, or stock prices, or anything that happens over time, you need to see the pieces one by one, in the right order, to ever have a chance of seeing the big picture.
So let's dive into that. Why is this such a tough nut to crack for traditional AI models? And why did we need a whole new way of thinking to solve it? Okay, this slide really gets to the heart of it. On the left, you've got your standard feed-forward network. It takes all its inputs in one big gulp. It has zero sense of time, zero sense of order. But on the right, you have the recurrent neural network, or RNN, and it's built completely differently. It processes things one at a time, in a sequence. And, this is the magic part, it carries what it learned from the last step into the current one. And because of that all-at-once design, the standard networks just completely fall flat on their face with this stuff. They have a very limited context. They can't remember something that happened way back at the beginning of a long sentence. This makes their design super brittle, and they usually demand a fixed input size. I mean, how often are sentences the exact same length? Almost never, right? So yeah, we needed a better tool for the job. And that new tool is the recurrent neural network. This is the architecture that was specifically invented to give our AI something that kind of looks like memory.
So what is it really? Well, at its core, an RNN is a neural network with a special trick up its sleeve, a feedback loop. This little loop is what allows information to stick around, to be passed from one step of a sequence to the next. And it's this persistence that acts as the network's memory.
Honestly, this feedback loop is the absolute superpower of an RNN. It's the whole game. Instead of information just moving forward through layers, like in a normal network, it also moves forward through time. A little piece of what the network is thinking at one moment gets fed right back into itself for the next moment. It's wild.
And to really get a feel for how this works, we can visualize it by unrolling the network through time. So look here, at time t-1, it chews on an input and creates something called a hidden state. Then, that hidden state gets passed to the exact same cell at time t, right alongside the next input. This just keeps repeating, and the key is that the same set of rules, the same weights, are used at every single step.
Okay, so it has memory. That's cool. But how does it learn what's important to remember and what it can just forget? Well, that brings us to the really unique way these things are trained.
It learns using a process with a very fancy name, backpropagation through time, or BPTT for short. But once you see that unrolled network we just looked at, it starts to make sense. It's really just a super deep feed-forward network where every layer happens to share the same weights. So when the network makes a mistake, the error signal travels backward through the layers, but it also travels backward through time, telling the network how to get better based on the whole sequence.
But that immediately brings up a huge question, right? If that error signal has to travel back through a sequence that's maybe hundreds or even thousands of steps long, what happens to it along the way?
Turns out it runs into two massive problems. They're two sides of the same coin, really. The first is called vanishing gradients. This is where the learning signal gets weaker and weaker as it goes back until it's just a whisper. The other problem is the exact opposite, exploding gradients, where the signal gets exponentially louder until it's just screaming nonsense and the whole model becomes unstable.
This slide shows the exploding gradient problem perfectly. Just imagine a weight in that feedback loop is a tiny bit bigger than 1, say 1.1. As you backpropagate through 100 time steps, you're basically multiplying by 1.1 100 times. And the result is this ridiculously huge, out-of-control number that just completely wrecks the learning process.
And of course, the opposite happens with vanishing gradients. If that same weight is just a little less than 1, like 0.9, well, multiplying that by itself 100 times makes the signal shrink down to practically 0. Poof, it's gone. This means the network basically becomes incapable of learning from things that happened way back in the past. It loses its long-term memory. All right, so keeping those challenges in mind, let's see how these things actually stack up in the real world. We're going to take a look at a case study on forecasting book sales. So the data for this comes from the U.S. Census Bureau. It's tracking monthly book sales from 1992 all the way up to March 2020. And you can clearly see these seasonal patterns, the spikes and dips. But also, look at that sharp drop right at the end. That's almost certainly the start of the COVID-19 pandemic. So this is messy, real-world data.
Now, to get this ready for our RNN, we have to do a little prep work. First, we take the raw data. Then we chop it up into a bunch of overlapping sequences of different lengths. And then, and this part is really important, we pad the shorter sequences with zeros so that every single input is the same length. You have to do that to train these things efficiently.
And after training for 100 epochs, here are the results. We're looking at a couple of error metrics here, but the main takeaway is this. The error on the test set is just a little bit higher than on the training set, and that is exactly what you want to see. It means our model is generalizing. It's not just memorizing the answers from the training data.
But this right here, this is the real payoff. When we put our RNN's performance up against a standard, plain old feed-forward network on the same exact task, I mean, it's night and day. The RNN, because it can understand the sequence and the context of the sales data, just blows it out of the water. This shows you so clearly, for sequential data, you have got to use the right architecture.
This all leads us to our final point, and it might just be the most important lesson of all when you're working with any kind of data that depends on time. This is the golden rule. You have to always split your data chronologically. You train your model on the past, and you test it on the future. That's it. You have to do this because it mimics how the model will actually be used in real life, making predictions about what's going to happen next based on what's already happened. And why is this so critical? Because if you just randomly shuffle your data, like you would with other problems, you're basically letting your model cheat. You're leaking information from the future into its training set. And you'll end up with a model that looks like an absolute genius during testing, but the moment you try to use it for real, it will fall apart. So we've seen how these recurrent neural networks give machines a kind of memory. It's what lets them understand sequences and make some pretty incredible predictions. This tech is already behind your phone's keyboard, your voice assistant, and so much more. Which kind of leaves us with one last big thought. If an AI can learn to remember the past well enough to predict the next word or the next month's sales, what else can it predict about our future?